So this, we are talking here about locus of the roots with P2. The denominator was this, or perhaps it's easier to arrange it as so. From this, you know that what is the sum of the roots of a quadratic equation? What will be the sum of the roots here? Minus P2. So as P2 comes to lower and lower frequencies, the sum of the roots becomes smaller and smaller. So either if one of them moves to a higher frequency, the other one has to move even more to a lower frequency. Or if they are complex conjugate roots, the sum of roots is basically the real part, twice the real part. So the real part keeps on decreasing. So that means that you keep getting slower and slower. Okay. Now, yesterday someone mentioned that the locus will be a straight line parallel to the imaginary axis. That happens if you plot the locus with k. Okay, that's also, in fact, that's what is frequently done in the root locus problems in control systems. You vary the gain factor and plot the roots. In that case, you see that the sum of roots is a constant, which means that the real part of roots is a constant, whereas the product keeps on increasing. So it will keep becoming, the imaginary part keeps becoming larger and larger. Okay. So in this case, anyway, the roots are okay. Is this correct? No. Oh yeah. This also, yeah. This is actually omega u P2 by k. Okay. So this part is minus omega square. That is, in the S plane, we plot omega versus sigma, and this is minus omega square when it is when we are talking about imaginary, roots having imaginary parts, and this is sigma. So we can see that minus omega square is nothing but sigma minus omega u by 2k square minus okay. So this gives us sigma square, that is p square by 4. Sigma is nothing but p2 by 2. So sigma, this gives you sigma square minus sigma times omega u by k. Is this correct? Or is there another factor of 2 missing somewhere? Should this be 4k or 2k? This. Yeah, it's correct actually. So the locus will be described by sigma minus omega u by 2k square plus omega square equals omega u by 2k square. So this is the radius omega u by 2k, and this is the center. Okay, that is its offset along the sigma axis, and the imaginary part is 0, right? And it describes a circle which has a radius equal to the offset, so the circle goes through the origin. Okay. So here is a neater plot of the same thing. So this is the root locus with P2. I have started off from some very large value of P2, that is 10 times omega u by k, and go all the way to very low value, which is about 0.1 times omega u by k. Omega u by k is the unity loop gain frequency or the bandwidth we would have had in the absence of P2, right? So I start from very high value. If I do that, then the poles are pretty much at minus omega u by k and the second pole itself. Okay. Whereas as I keep on reducing the value of P2, this arrow direction shows a reducing value of P2, not increasing values. It comes here, and then here at minus 2 omega u by k, you have two identical real poles. After that they split and they move this way and that way. Okay. And here the sigma and omega axis are normalized to omega u by k. So this 1 means that it is omega u by k. Any questions on this? Okay. Omega u by k, which one? No, center is at omega u by 2k. So if you look at the plot also, oh no, center is at omega u by k. 1 second. So did I get the constants incorrect here? Omega u by k. Which one? Sigma plus. Why? Oh yeah. What was the, let me rewrite the equation for the roots. Okay. So this part is minus omega square. That we all agree on, right? So sigma is minus P2 by 2. And minus omega square. No, if I do this, I do get why? I mean, I'm just expanding this. What's that? Sigma square plus? Oh yeah, this is minus P2 by 2. Sorry, that's correct. Yeah. Yeah, that's right. I messed up the normalization. So this is correct? No? Yeah. So the radius is omega u by k and the center is minus omega u by k on the real axis. Okay, thanks. So this is just to show how the poles move with P2. You can see that the real part keeps reducing, which the real part is what governs how slowly the response decays, right? Even if the roots are complex, the decay of the response is given by exponential of minus real part of the root times t, right? So that determines how slow it is. So it will keep getting slower. But there is one sweet spot where you can, yesterday I showed for sinusoidal steady state response, that is the magnitude response, bandwidth can be extended if you have the pole set 45 degrees from the real axis. That is, you try to make a maximally flat magnitude response. Okay. So any other questions on what we have done so far? Feedback systems and analysis. So we have seen that with the feedback system, we can control the output to be some function of the input. For our case, we are concerned with linear functions, that is trying to make amplifiers, but it doesn't have to be. It can be some nonlinearity also. Now, to do that, we need an integrator, but we can't make an exact integrator. We will have a finite DC gain, that is the non-ideality on the low frequency side. And also, the response will not be minus 20 dB per decade at very high frequencies. It will have a higher slope because of parasitic poles. Okay. So, because of that, we get some other non-ideality that we saw was equivalent to delaying the response around the loop. That is basically delaying the loop gain response. So that can push the system towards instability. With only two poles, that is one pole at the origin and an additional pole, you will never have right half plane roots. But if you have more poles, you can have right half plane roots also. Okay. And as far as amplifier design is concerned, we would like to design the system with either no ringing or just a little bit of ringing, and again either no peaking or maybe just a very small peaking in the frequency response. Okay. So we will certainly not want the imaginary part of the poles to become very large compared to the real part. Even if it doesn't become unstable, that's not a condition that we would like, because that if the imaginary to the real part is large, that implies a very high quality factor. That means a very high or very low damping factor. So that means also a high amount of ringing in the step response. Okay. And we also along the way saw the importance of loop gain. So if the loop gain is frequency dependent, where it is large, you get nearly ideal response, and where it's small, you get quite non-ideal response. So the loop gain, where the loop gain crosses unity, is a kind of breaking point between the ideal response and the non-ideal response. And as far as the DC loop gain is concerned, that determines the relative accuracy. The relative accuracy of the DC gain of the closed loop system is the inverse of the loop gain. Okay. Now, so far, I have acted as though all the non-idealities will be here. Okay. Now, you can have additional poles because of the feedback path also. So, a very simple example is, how do you realize an attenuator of 1 over k? So, the simplest thing you can think of is a resistive divider, right? So, if you apply V0 here you get V0 divided by k. So, can you have a pole in this? How? If we have a parasitic capacitor here, there will be a pole in the response between the input of the voltage divider and the output of the voltage divider. Okay. So you can have parasitic poles because of the feedback network also, and in reality this does happen. Okay. Both the forward path and the feedback path will have parasitic poles. So before I put all of the parasitics in this, but it's really the parasitic pole in the entire loop gain that matters for the stability of the system. Okay, not really the forward path alone. So, if ideally we would want the loop gain to be to be some ideal integrating function. I'll call it omega u loop by S. In our particular case, omega u loop was omega u of the forward path integrator divided by the feedback fraction. Okay. Now, in addition to this, you can have a second pole and a third pole and so on, and you can also have zeros also, depending on the circuit realization. But all of these should be such that, so let's say if you have only poles, then the loop gain magnitude plot should look like this. This is omega u loop, and all of the parasitics should be beyond omega u loop. Okay. Now similarly, just like we analyzed before, you can add left half plane 0 to compensate the effect of some of these parasitic poles. Or if you do have right half plane zeros, then they have to be also well away from the unity gain frequency. Okay. So the loop gain has to have this first order behavior up to a point where it goes below unity. Well beyond the point where it goes to unity, you can have parasitic poles and zeros, and they won't affect the system too much. Okay. They do have an effect on the system, just like we have analyzed, but if they are well away, then they don't have any effect. Okay. So whenever you design a feedback system, this is a criteria that you have to follow. That, and also, on the DC side, the loop gain has to be large enough. So in reality, you will not get this. It will flatten out somewhere. Now it can flatten out at a lower or a higher value. That gives you lower or a higher accuracy. Okay. So depending on the accuracy, you have to design the DC loop gain, and depending on the speed, you have to design the unity loop gain frequency. And given the unity loop gain frequency, you should push the parasitic poles and zeros beyond that. Okay. So, and those are the basic specifications. When you are asked to make a system, you will be given the accuracy and the speed. Okay. From that, you will have to design all of these parameters of the circuits. Now, a frequently used term, we didn't even talk about things like phase margin, but it's a related quantity. Okay. So we did the analysis, the complete analysis in the frequency domain and some in the time domain to figure out what's happening to the feedback system. And from that came to the criteria that to get critically damped response, the second pole has to be 4 times larger than the unity gain frequency of the loop and so on. Okay. So let's take a case where the loop gain is an integrator and another parasitic pole. Okay. So for critical damping, P2 is 4 times omega u by k, and for maximally flat magnitude response, P2 is 2 times omega u by k. Now, a similar thing, the effect of the parasitic pole can also be expressed by looking at the phase of the response. Okay. So this is omega u by k, and this is P2. Okay. Now this is the magnitude of the loop gain. Okay. So maybe I should write. Now if I plot the angle of the loop gain, what does it look like? What is the angle of the loop gain at very low frequencies? minus 90. So you have omega u by ks, that is j omega. It's imaginary number with a negative imaginary part, so it's minus 90 degrees. Now what happens if I keep increasing the frequency? Huh? What is the phase? So at P2, it will, an additional pi by 4 will be added to it. So maybe I'll exaggerate this a little bit. Okay. And asymptotically it will go to minus pi. Right? Now, you are supposed to make a negative feedback system, and the way the system is defined, if L is positive, it is negative feedback. So if L has a phase angle of pi, it is positive feedback. So phase margin is a measure of how far away it is from this positive feedback condition. Okay. So this phase, that is the phase at the unity gain frequency, unity loop gain frequency, away from 180 degrees, this is the phase margin. How much is that for this system? No, I mean not the value, in terms of P2 and the P2 and omega u and so on. What is the phase margin? Huh? Tan inverse omega u by kp2. So if P2 increases, the phase margin decreases. So see, this is the total phase shift introduced by the system. The angle is pi by 2, minus pi by 2 because of the integrator, minus tan inverse of, and we are looking at this frequency. So it is omega u by k times P2. Okay. Now this is the phase angle, and we want to see how far this is away from pi. Okay. So this plus pi, basically it is pi by 2 plus tan inverse omega u by kp2 minus. So this is nothing but, I mean, if you shift it away from pi by 2, you will get the reciprocal of the inverse tangent, right? So tan inverse of kp2 by omega u. So if P2 is very large, if P2 tends to infinity, the phase margin tends to 90 degrees. That you know, right? Because if this factor, extra factor disappeared entirely, the phase would be constant at minus pi by 2, so the phase margin will be pi by 2. Okay? So the phase margin for this system is tan inverse of omega u by k times P2. Okay. So for critical damping, you need so instead of using, if you cannot calculate the value of the pole, what is done in simulation is to plot the magnitude and the phase response, and to look at the phase where the gain crosses unity. Okay. So because when you are simulating it, you may not know exactly where the poles are. You can do pole zero analysis, and that can give you some problems as well. So you try to do it by evaluating the steady state response. In that case, the same criterion can be stated in terms of phase margin. Okay. So for this, what is the phase margin? It's tan inverse of 4, right? How much is that? And in this case, it's tan inverse of 2. So tan inverse of square root of 3 or 1.7 is 60 degrees, right? So this is more than 60 degrees. probably 70 or something of the sort, and this is even higher than that. Okay. What's that? Yeah. So, sorry. So, is it 1 by 4 or? No, it is correct. So Kp2 by omega u. As P2 increases, phase margin improves. So, to get maximally flat magnitude response, you need more than 60 degrees of phase margin. Okay. And to get no ringing at all, you need probably more than 80 degrees of phase margin. I forget what tan inverse of 4 is, but I think it is something close to that. So this is mainly done with simulation, but you should realize that all these are only approximate things, because in reality you will not have just one pole and so on. So this translation of what is critical damping to what the phase margin must be, all that is approximate. Okay. But you can be sure that if you have a phase margin close to 90 degrees, you will have a response with no ringing or no peaking in the frequency response. Okay. And this is a criterion that's widely used in simulation. Okay. Yeah. Yeah, that is this. No. The phase margin is pi by 2 minus tan inverse of omega u by Kp2, which is tan inverse of Kp2 by omega u. Okay. Yeah, see, for a second order system, you can clearly define quality factor, you can define phase margin also, so you can clearly do all of this, right? So first of all, I can, given P2 and omega u, I can find the quality factor. So instead of using P2 and omega u, I can use omega u and the quality factor, for instance. Okay. It may be a complicated function, but you can certainly relate. Rather, in fact, the Q factor is a function of omega u divided by Kp2, right? What was it? Square root of omega u by Kp2. Is this correct? So this simply is tan inverse of 1 over Q square, that's all. But the problem in reality is that you will not have a second order system. So the notion of quality factor and so on is not very precise. Okay. But we do know that if things happen well beyond the unity loop gain frequency, then the result will be more or less a first order system with additional poles at at these locations. Okay. So what I mean is, we already saw that if this is the factor that multiplies all of the ideal gain functions in a feedback system, okay, in any transfer function. You take any input and any output, you will have this. So this is equal to 1, approximately equal to 1, when the magnitude of loop gain is much more than 1, and approximately equal to L if magnitude of loop gain is much less than 1. Okay. So if you have a loop gain function like this, where all of the parasitic effects are at high frequencies well beyond the unity loop gain frequency, then the resulting function will simply follow a first order type of behavior until you see these parasitic effects. Okay. So you do know that if you place all of these parasitics very far away from unity gain frequency, you will get more or less a first order behavior. The question is what happens when you get closer to this. Now the real answer can be found only by looking at the poles, but that may be difficult because we may not be able to find the parasitics, the analysis may be too complicated and so on. And with the simulator, it's much easier to put in sinusoids and see the steady state response, not so easy to calculate the poles. Okay. So in that case, you come up with approximate criteria like phase margin. So you first do an analysis for a second order system and then you somehow relate it to the others as well. Okay. But again, if the parasitic poles are very far from unity gain frequency, we already know that again the phase margin will be 90 degrees. So we say that if the phase margin is close to 90 degrees, you are very safe. Maybe 60 degrees and above is okay, something else. No, first of all, again, this is the plot of the loop gain. Okay. So if the loop gain has complex poles, and if the poles are far away from the unity gain frequency, this is still true, right? Because this is just this just depends on the magnitude of L. This is a mathematical approximation. So if you happen to have complex poles here, maybe the response will not follow this, it will follow something like this. But that is still, these things will still remain true. Okay? Now, if the, now what is the question? Is the concept of phase margin valid or what is the? Yeah, then, in reality, in the closed loop, if the loop gain has complex poles somewhere here, then what will probably happen is that when you put it in closed loop, they will move into the j omega axis. They will probably move closer to j omega axis and in some cases move into the j omega axis as well. Okay. So it's like the system is already, a system with complex poles, you can think of it as being more unstable than a system with real poles. Okay. It has a greater tendency to ring. Now if you put that in a feedback loop, it will probably push it all the way into the right half plane. Okay. Yeah, but your phase margin will be very bad to begin with, right? Meaning, if you had complex poles in the loop gain, so let's say the loop gain, poles, like we started off with something where one of the poles was here and the other pole was somewhere far away, right? So instead of this, let's say you start off with something which has some stuff like this. So then the phase margin will be very poor. It is valid, but it will give you a very poor result because with this and this we are saying is below the unity gain frequency. Now we can't even define the unity gain frequency properly, right? If you have complex poles. So maybe you will have 3 poles. You have something like this and these 2. Okay. So perhaps the loop gain would have done this. Because of the complex poles, it will give you some peaking or something of the sort. So what will happen in the phase domain? It would start from minus 90 and with 2 complex poles, you can go to minus 270, right? So something like this. So when it crosses unity, it's already very poor. Okay. It is valid, but this is not a very useful system. So the phase margin is in fact telling you that it is going to be unstable. But I want to emphasize that phase margin is not an exact criteria. The ultimate test is to find out, using root locus or Nyquist plot, basically to find out where the poles are. Okay. Anything else? Where? Yeah. Yeah. No. So the question is, if the gain is more than 1, when the phase is 180 degrees, is the system unstable? But not necessarily. Okay. Because you have systems where, so let's take something of this form, okay. something that has 2 zeros and 3 poles, and there can be some constant in front of it. Let's say the Bode plot looks something like this. So what is the slope initially? Minus 60 dB per decade. Okay. And what's the slope after Z1? Minus 20 dB per decade. So if you look at this, this is the 0 dB line. If this is the loop gain, the phase, what does the phase do? So minus 270, and at what is the phase at Z1? Minus 180, right? Isn't it? So now if you look at it, all these points, I mean the minus 180 occurs here, right? And the gain is more than 1. But this system is stable. Okay. So you can't say that if the gain is more than 1, when the phase is 180 degrees, the system is unstable. So the analysis of stability gets complicated if the open loop system or the loop gain has zeros. So if the loop gain doesn't have zeros, then so let's say if the loop gain has only certain number of poles. So in this case, the loop gain will go down monotonically with frequency, and the phase will also go down monotonically with frequency. In this case, by looking at the phase margin, you can make some reasonable statements about stability. But if you have zeros also, things start getting complicated. Okay. Gain is 1 and I think that is unstable, but I don't know. There may be exceptions. I am not 100% sure. So this is the opposite condition. The question is, if the gain is 1 and the phase lag is more than 180 degrees, is the system unstable? I think so. I'm not sure actually. Maybe not. I don't know. The sure thing is, if the gain is 1 and the phase is 180 degrees, the system is certainly unstable, because you get 0 in the denominator, you get infinite gain. But yeah, I mean the concept of phase margin is based on what you're saying, that if gain is 1, you look at the phase, if it's more than 180 degrees, you say it is unstable. But I don't know if there are exceptions to that. Okay. So if you have all pole system, that is definitely true. That if gain is 1 and phase is more than 180 degrees, it is unstable. And for an all pole system, the other way around is also true, because the gain and phase are monotonic. If the phase is 180 degrees and gain is more than 1, then the other condition is also valid and it will be unstable. Okay. But when you have zeros and so on, I don't know if you can come up with a system where the gain is 1, phase is more than 180 degrees, but somehow the system is stable. I'll think about it. Any other questions on what we have discussed so far? So let's take this feedback system and modify it slightly. Okay. This is just to convince you that the loop gain remains the same regardless of where you put the input and the output. So in this case, I will put the pole in the feedback path. Okay. This is just to make the transfer functions more interesting, but nothing special about this. Okay. Now I feed the input here normally. Okay. I can also feed another input here. Okay. And I can think of this as my output, or maybe I can think of this also as my output. I mean, anything is an output and anything is an input. Okay. So what is V0 by Vi? Huh? What is the general form of the gain of the transfer function of a feedback system? G by 1 plus GH, where G is the forward path gain and GH is the loop gain. Okay? Or the alternative form is 1 over H times 1 over 1 plus 1 over GH. So what is the, can you quickly say what the transfer function is? So you get 1 over H, so you get the reciprocal of this one. Okay? 1 plus S by P2 divided by the denominator polynomial, and this is something we have seen many times, right? It's not visible. Okay. What is V0 by V1? Okay. So, if you, I mean, do you get d of s in the denominator and some polynomial in the numerator? G is 1. So, I mean, see, like in some cases that 1 over h times that is the easier form to write, isn't it? So, this is k times s by omega u 1 plus s by p2 divided by d of s. Is this correct? And what is V2 by V1? So I'd like answers from this side of the class. I think it's been too inactive for too long. What's the answer? What is V2 by V1? What is the answer? Yeah? K, no, just the numerator. Let's say, did you get the denominator to be the same denominator or no? So what is the numerator? S. S by omega u, I think, actually. So for V1 to V2, the feedback is this, okay. This is H for the transfer function between V1 and V2. And this is G, okay. So 1 over H is S by omega u. And the denominator is still 1 plus 1 over GH, okay. So it's S by omega u divided by d of s. And finally, for completeness, what is V0 by, sorry, V2 by Vi? V2 by Vi is the same as V0 by V1. That's correct. Okay. Because it looks like the same thing, right? V1 is added and you take the output from there, and similarly Vi is added and you take the output from there. Okay. So this is, let me move this to the side. So this is also equal to V2 by Vi. So you can see that the denominator polynomial, and hence the poles and quality factor, all of these things are the same for all transfer functions, regardless of where you feed the input and where you take the output from in a feedback system. Okay, the numerator does change, so the zeros do change. So for instance, this is a what kind of transfer function is this? Huh? It's a bandpass system. Okay, so at very low frequencies it's 0, and very high frequencies also it is 0, because the denominator has a square. What is this? What is this transfer function? What kind of transfer function is it? Is it high pass, low pass, or band pass? Band pass. So, I mean, I call it a high pass if it has a non-zero gain at high frequencies. Okay. In this case, the numerator has a square and denominator also has a square. So, it becomes a high pass system. So, the high frequency gain is unity. Now, it's not very hard to figure out why, right? So, we are talking about this path, V1 to V0. Okay. What happens at very high frequencies to the loop gain? I mean, it's, see, at very high frequencies, this path attenuates and this also attenuates. So basically, whatever goes around the loop is nearly 0. At extremely high frequencies, it's like the loop is broken. Okay, so you have a direct path from Vi to V0. So whatever you evaluate, that should come out to be 1 at very high frequencies. Okay, because we know that the loop will be broken at very high frequencies. Not broken in the sense of physically breaking connection, but broken because whatever you feed here, nothing comes back here. Okay, the signal magnitude is very small. So similarly, if you look at the transfer function between Vi and V0, at low frequencies there is active feedback, but at very high frequencies the feedback is kind of broken. So it simply goes through omega u by s. Okay, so that's what you expect. And at very high frequencies, of course, it becomes 0. So this is a low pass kind of function, or low pass with a 0. This is high pass, this is band pass, and you can get all kinds of exotic combinations. And also you can inject the input to different points, right? I can say that I'll inject the input not only here, but I also connect it here. Okay? So I can do this. So then what will I get? What will be the transfer function between V0 and Vi? Huh? Sum of the two, right? Because I have, when I put it here alone, I get this. When I put it here alone, I get this. So when I put it in both places, I get the sum of the two. Okay. In this particular case, it may not be interesting, but in some cases, you can get interesting transfer functions by feeding it at multiple points. Okay. An alternative thing is you can take multiple outputs and sum them. Okay, that also gives you sum of different transfer functions. So if you want to manipulate the zeros, that's what you do. Okay, you either first look for different points to inject the input, or different points to take the output from, or you inject the input to multiple points, or you take the output from multiple points and form a linear combination. Okay, so when you are forming transfer functions, this is how you do it, if all you are interested in is manipulating the zeros. If you want to manipulate the poles, you have to change something in the loop. Okay, is this okay? So to manipulate the zeros, you don't have to do anything to the loop itself. Okay. So this definitely you should keep in mind, and when you get answers and so on, so maybe in some particular case you are required to analyze different transfer functions in a loop. You have to get them to have the same poles. Now there can be occasionally weird cases where when you have a particular zero, that will cancel with a particular pole and give you a different transfer function. But beyond that, you can't get something totally different. Okay. And this is also a design tool to get to synthesize different types of transfer functions. You use this. Okay. So what we'll do on Friday is to start using op amps to realize these feedback structures. Okay.